We want mathematical definitions for the hypersurface so that we can locate the minimum, whether it's reactant, product, and even the settle point through some mathematical definitions rather than scanning the entire potential energy surface diagram. And this is particularly challenging if we talk about system with hypersurface. So how can we do that? We know that reactant, products, and transition states are stationary points on the potential energy surface. Mathematically, a stationary point is defined through first derivative of energy with respect to displacement. So if you have a system where the first derivative of energy with respect to displacement in all direction is equal to 0, that is known as a stationary point. So it means derivative of energy with respect to displacement in all direction Qi should be equal to 0 for a stationary point. So there are different kinds of stationary points. Reactant and products are local minima, whereas transition states are saddle point. These are called saddle points because they look like saddle. The local minima, they are minimum in all directions, and they are the lowest energy minima on the entire potential energy surface is called global minimum, whereas a minimum with energy higher than global minimum is called as a local minimum. Now, the saddle point is a maximum in one direction, and that is reaction coordinate, whereas this saddle point is minimum in all other surfaces. So transition states are saddle points, and they are maximum in only one direction, and they are minima in all other directions. We said previously that we can identify reactant and products structure on the potential energy surface. Now, in the case of local minimum, the first derivative is 0. For saddle point, first derivative is 0. For all Qi, it's also for all Qi. So that is a stationary point. So when you have the derivative of energy with respect to displacement, which is actually talking about the forces there, it should be 0. So it means when the forces on the nuclei are 0, the system considers the structure as a minimum. It can be a local minimum, reactant or product, or it can be a saddle point. But this minima and saddle point, they can be differentiated from one another based on the second derivative. We said that the first derivative of energy with respect to displacement is actually a force. So it means for local minima and saddle point, forces on the nuclei are 0. But to differentiate between local minima and saddle point, we have to consider the second derivative. Now, in the case of local minima, the second derivative is positive for all Qi. The second derivative is positive in all direction. And you can see here, if you're starting looking at this reactant here, our product, if you start moving from this reactant, you have to go uphill. You have to go uphill in any direction, starting from reactant or even from product for these minima. If you start moving from here, you have no other option except to go uphill, no matter whatever the direction you move on. Similarly, from this product here, in any direction you move, you will have to move the uphill. So it means the force constant or the second derivative should be uphill or positive for these minima. And this is what mentioned here. The second derivative is always positive for a local minimum. On the other hand, saddle point is something different. The saddle point is this one here. Now you can see here in one direction, which is the reaction coordinate. If you start moving from the saddle point, you go downhill. So it means in this case, the force constant along this direction should be less than 0 because you're going downhill. But in all other direction, it should be positive. So it means a saddle point can be characterized With the second derivative, in that case, one value should be less than 0. Less than 0 means it should be negative curvature in one direction for exactly one qi, which is the reaction coordinate. And it should be a maximum along that direction. Whereas all other values of the second derivatives are positive. So it means for transition state, one value of second derivative is negative, whereas all other values are positive. But for minimum, all values are positive in all directions. So second derivative is actually reflecting the force constant, and the force constant is negative in the case of transition state in the direction of reaction coordinates, whereas minima, whether it's local or global, the second derivative, which is reflecting the force constant, it should be all positive. So that's how you can differentiate between a minimum and a saddle point. Okay, now we move on to the geometry optimization. Now you need to understand what does the word optimization mean. Optimization means that to relax the structure to the most stable structure. So it is a process for locating a minimum or transition state on potential energy surface. It's also called relaxation, at least for finding minima. The most common type of calculation performed in computational chemistry. No matter whatever the system you plot in, the first step is to optimize the structure. Why we need to optimize? Because every person has different way of drawing the structure on computational softwares. It might be possible that the structure I draw for any molecule may be different than the structure probably you're drawing. So if the structure I draw is different than the structure that you draw, it means that the properties calculated on the structure that I have drawn will be different than the properties calculated on the structure you have drawn. And now in that case, it will lead to some problem because the results will not be reproducible. To avoid these problems, first you need to optimize the structure because the software taking the structure drawn by yourself into account, and it will try to find the lowest energy structure near it, and that process is known as the optimization. So any property you calculate on a structure drawn without optimization will be non-reliable. So it means first you have to optimize the structure before you can calculate any properties. So that's why this is the most common type of calculation performed in computational chemistry. So why we need to perform optimization? Because to determine the reaction mechanism and associated energetics, to determine preferred molecular geometries for calculation of other properties. This is what I mentioned right now. So the basic idea is that it's an iterative process. The structure that you give to the software will take that structure and it will perform a set of calculations, keep on changing the structure, again performing some set of calculation, and finally coming to the minimum or a transition state. It starts with a guess structure, the structure that you give to the software based on your own drawing, and it uses information of the potential energy surface to change the coordinates such that the final structure is a stationary point. Let us find minima or transition state without any exact information regarding those points on potential energy surface. And the method used here is called Newton-Raphson method. Before moving on to the Newton-Raphson method, you need to know the difference between harmonic potential energy surface and anharmonic potential energy surface. For this one, I will have to take you back to the example of nitrogen. Now, you can see here in this potential energy surface, this is the stationary point, and the surface on the left side of the stationary point is not matching with the structure on the right hand side. So it means if you take the vertical line here on the stationary point and you see the left hand side and the right hand side, they are not looking similar. So in that case, this surface is known as anharmonic surface. And bear in mind that all surfaces for real systems are anharmonic in nature. But the problem in computational chemistry is that we are always starting and assuming that the potential energy surface is harmonic. Now you can see here, the potential energy surface drawn here is harmonic, because let's say if this is the minimum and you draw a vertical line here, then the left hand side and the right hand side, they are looking identical. So if you're considering 1D harmonic potential, in that case, let's say you draw the structure which is somewhere on this point on the potential energy surface, and this is the ideal equilibrium structure or the structure of the stationary point. Now, this is your initial input structure, and its coordinates are qi and the energy is ei, whereas the minimum has coordinates of q naught and the energy of E naught. How much is the difference between these two? The difference in energy between this E I and E naught is equal to K Qi minus Q naught square. And this is actually coming from the Hooke's law, that the change in energy is actually depending on force constant into difference in displacement square. And if you take the derivative here, this 2 will come here. It will become 2k qi minus q naught. If you take the second derivative, you can see the second derivative of energy with respect to these coordinates is equal to k, 2k, which is force constant. And now, if you rearrange equation and substitute the value of 2k, this value of 2k inside this equation, you can ultimately get q naught is equal to qi minus first derivative divided by second derivative. If that's the case, if you know the surface is harmonic, you know the first derivative and second derivative, you can jump from any gas structure to the minimum in just single step. You can find minimum in just one step from any given structure if the surface is perfectly harmonic. But in reality, surface is never harmonic. In general, potential energy surface is not harmonic. So the implication is that you cannot find Q naught in one step. Instead, we iterate until the forces on nuclei are very small. So we will take the equation on the last slide, this one, and do step by step. Qi plus 1 is equal to Qi minus first derivative divided by second derivative. Similarly, for the second part, Qi plus 2, now in this case, Qi plus 1 is depending on Qi, but Qi plus 2 is depending on Qi plus 1, because for Qi plus 1, the initial input is Qi. This one, when you're talking about the second point, you're taking this one as a reference. But when you're taking the second calculation here, now your reference is I plus 1. So Qi plus 2 is equal to Qi plus 1 minus first derivative divided by second derivative. So at the end, you can have n number of such calculation, where nth calculation is depending on n minus 1 minus first derivative divided by second derivative. So now we iterate until the forces on the nuclei are small. So these forces, this first derivative is force and second derivative is force constant. So the first derivative should be getting small enough that it is approaching zero. Once it is approaching zero, we can assume that the structure is optimized. With a reasonable gas structure, most programs will find the nearest local minimum in 10 to 20 iterations. It means if you give a structure to the software and software can optimize it in the next 10 to 20 steps, it means your guess structure is quite good. But if the software is taking more than 20 steps, it means probably your input structure is not that much good. This is true for minimum, but for the transition state, the situation can be quite complicated. The optimization of transition state requires even more skills and these are more difficult to locate.